10.3 Projectile Motion Examples. A projectile's path can be described by a parabola. A parabola is a curved path that is symmetrical on both sides. It is typically seen on a graph describing the relationship between y and x squared. At all points along the path of the parabolic trajectory, you can find the total velocity by combining the Vx and the Vy components. Every moment along the trajectory has a different velocity triangle. This is the triangle created by combining the x and y components into a total velocity vector. Every moment has the same Vx because Vx is constant, but Vy is different because Vy is affected by the acceleration due to gravity. Vy decreases as it goes up and increases as it goes back down. Because the velocity of each moment is described by a triangle, you can find the magnitude of the velocity by using v equals the square root of vx squared plus vy squared, and you can find the angle it's at by taking tan negative 1 of vy divided by vx. At the peak of a projectile's path, it's the transition point between the projectile traveling in an upward direction and traveling back downwards. At the exact moment when it changes direction, the Vy is 0. And the only component is Vx. Vx remains constant because the projectile's x velocity is always constant, but the Vy has been reduced to 0. So at the peak point, we might also call this the maximum height. There's only Vx because Vy is 0. Just before, the velocity was traveling up. And after, the velocity starts traveling down. We can use this fact to calculate the maximum height of a projectile. Here's an example that shows how to do this. A projectile is launched at 30 meters per second, 10 degrees above the horizontal, from the ground. How high does it go? We start by drawing a picture. The projectile is being launched with this Vi at an angle. It travels up and back down, and we're only interested in this halfway point for where Vy equals 0, so we can find out the maximum height. This is the vertical displacement. On our xy table, Vx is equal to the cosine of the angle, 30 times cosine 10, and Vy is equal to the sine of the angle, or 30 sine 10. In the y direction, we know that Vf equals 0 at this maximum height we're looking for, and the acceleration is always equals negative 9.81. We don't really even need to consider the x side for this case. This is because we're only interested in the vertical displacement and we have all the vertical information we need. So we only write down the x side to just acknowledge that it's there, but it's not really necessary for the solution. For the y direction, we can use the formula Vf squared equals Vi squared plus 2AD, which rearranges to become d equals Vf squared minus Vi squared divided by 2a. Plug in all the values that we know. And you get dy equals 1.4 meters. And since it's positive, we say that it's up. Here's another example that will make use of the velocity triangle at a later time in a projectile's motion. A ball is tossed at 13 meters per second, 15 degrees above the horizontal, from the top of a 100-meter cliff. How fast is the ball going when it is 30 meters from the ground? It is always helpful with projectile motion to draw a picture of the situation to get an understanding of the different values that are known in the problem. The cliff is 100 meters high, and the ball is tossed 13 meters per second at an angle of 15 degrees. It takes this parabolic trajectory of a projectile, and we are interested in how fast it's going 30 meters from the ground. At this time, the displacement from where it started is 100 minus 30, which is 70 meters from where it started. And we want to know the velocity of the projectile at this point. We start by making an xy table, where Vx is equal to 13 cos 15. Vyi is 13 sine 15. The vertical displacement at the point we're interested in is negative 70 meters, negative because it's down, and we're interested in finding out what is the velocity in the y direction at this point so we can combine it with the x velocity to find the total velocity. Vyf squared equals Vyi squared plus 2ad. This means Vyf equals the square root of Vyi squared plus 2ad. And it's important we remember to put a negative in front of the square root. This is because we know that the projectile will be traveling down when it's at our location. This means that Vyf is 13 sine 15 squared plus 2 times negative 9.81 times negative 70. Both these negatives are really important. Make sure you don't forget them, because if you forget them, it's going to change the value of the problem. The two negatives cancel out to make a positive. Vyf equals negative 37.211837 meters per second. And the negative gets changed to down to represent the direction. Now we're not done yet. This is just the velocity in the y direction. And the problem is asking us for the velocity of the projectile. The velocity of the projectile at this time is the combination of the x velocity and the y velocity. combine Vx and Vy, first we note that Vx is constant, so it's still 13 cos 15 as it was at the beginning. And we found Vy to be 37.211837 meters per second down. The magnitude of the velocity is calculated using Pythagoras' theorem. The square root of Vx squared plus Vy squared is the square root of 13 cos 15 squared plus 37.211837 squared, which is 39 meters per second. The angle is tan negative 1 Vy over Vx, which is 37.211837 divided by 12.55704, or 13 cos 15, which gives us an angle of 71 degrees down of forward. And since down of forward sounds silly, usually we write this in a different way. It's 71 degrees below the horizontal. So when we're asked what the velocity of the projectile is 30 meters from the ground, we say it's 39 meters per second at 71 degrees below the horizontal.